Okay, so that's it. So good afternoon. This is a session to solve a Nonsway frame using beam stiffness matrix as part of, I believe this is I think this is already considered as special analysis techniques because using just beam formulation stiffness matrix, we're now able to analyze frames. Okay. Oops. Okay, so since non-sway due to the lateral strain here, so since downward load, we have downward load here. So I can assume a curve something like this and something like this. So this has rotation here. Yeah. Then the column will reflect like this. Maybe something like this. Okay. So that's the assumed displacement curve. Now for the degrees of freedom, so I'll make this, okay, say this is 1, rotation 2, then this is 3, rotation 4, this is 5, rotation 6, this is 7, rotation 8. For the column, so based on the video, no, our convention is bottom up from bottom here. So this will be 7, 8, 9, rotation 10. Okay, this will be 11. But there, since we have a common rotation on this joint, so this is 4. Next is, this is 12, rotation 13, then 14, then rotation 6. Okay, and now let's write down each element stiffness matrix. So we have K1, K2, K3, K4, K5. Wherein, okay, so this is 1, 2, 3, 4. K2 is 3, 4, 5, 6. K3 is 5, 6, 7, 8. K4, 9, 10, 11, 4. Okay, be conscious on that. 5, 12, 13, 14, 6. Okay. What about our structure stiffness matrix? So how many unknowns do we have here? So I have an unknown this rotation here, unknown rotation here. Okay, no sway, right? So no lateral displacement. So what else? Here, unknown rotation here, which corresponds to 4, 6, and 8. So our expected size of S is 4, 6, and 8. So, sorry, 3 by 3 with codes 4, 6, and 8. So we will need to extract, no? Extract the elements for 4, 6, and 8. This is 4, this is 6. Okay? Okay. So that's it. Siguro I will allow you to to look at it for 10 seconds before I proceed to the SMAT. Okay, so let's now proceed with our BU and BB matrix. So I guess you can now realize the the importance of these parameters. No, it spares me from uh, spending time too much on getting all these elements in Excel. Although you can you can use Excel. No, if you search on even in YouTube, I'm finding lots of videos utilizing Excel. Although on my part, for me, it's using SMAT is more teacher friendly, no? Because you can see the formulas. That's what. So let's see. So member one, fourth element. Fourth. Member two, second and fourth. Member three, second and fourth. Member four, fourth element here. And last, member five, fourth element again. Last. So for the BB, we're in the destination. What's the location of four of this here? Four going to our S. It's on the first, right? So this will be one. Location of four and six to our S, first and second. Location of 6 and 8 to our S, second and third. Okay. Location of 4 here to our S is on the first. And last, the 6 here is on the second. I wish this has no mistakes. Okay. Next is our QF. So as you will observe, you have one, two, three. Three members with a two members with a uniform load and one with a concentrated load. So maybe here. QF1, QF2. QF1, QF2, and then QF3. QF1 is 1, 2, 3, 4. QF2 is 3, 4, 5, 6. And QF3 is 5, 6, 7, 8. So we can now have our PF. First, QF1 is 30 kilonewton per meter and length 4 meters. We know it's 30 times 4 over 2, that's the concentrated load. Where is my 30 times 4 over 2? 60 kilonewton. Okay. And since this is symmetric, this is also 60 kilonewtons. The moment, WL squared over 12. No. So that is 40 kilonewton meter. 40 kilonewton meter. So I'll just copy this here. QF2. Maybe, let's proceed with QF3. QF3, 40 times 3 square over 12 is also 60. And this is also 60. No, no, no. 40 times 3 is 120. Divide 2, 60 kilonewton as reaction, vertical. Moment, 30 kilonewton meter. 30 kilonewton meter. So this is also 60, negative 30. For QF2, let me write this as WL squared over 12. So here, this is PAB square over L square, while this one is PBA square over L square. That's the formula. So I've computed that. That is 80 and 60. Okay, this should be 80 and this is negative 60 for the moment. For the reaction, it's 66.667. Please check if there's an error. Then this one is 23.33. Makes sense because 90 is nearer on the left fixed end. So that's it. Then let's now extract the QFs to determine our P sub F. Which is 4, 6, and 8. So I'm going to extract this, and this, and this. Okay. So PF 4, 6, and 8. So all four, this one and this one, negative 40. Wait, 3, 4. Sorry. Negative 40 plus 80. So negative 40 plus 80. That is positive 40. Okay. For number 6, negative 60 plus 30. So negative 30. And for number 8, negative 30. So that's our PF. Okay. Where's our SMAT? So this is our SMAT. So we have, let me minimize this. One, two, three, four, five. So we have 5 members. Okay. So I'll be expanding this to 5 data. 2, 3, 4, 5. With length 463. This should be 4. Should be 6. 3, 4, and 4. 4, 4. What's our elasticity? No, no, not that. Let's assume constant. So 200 is okay. Next is inertia is you only have I. So we can assume any inertia. So make this 5, 2, 3, 4, 5. 300, 300. Mm, second is 2I, so this will be 600. Okay. I, so this will be 300. S is 3 by 3, so I'll make a null matrix size 3 by 3. Make this 0. Okay, then BU is here. Okay, 4, 2, 4. So I'll expand this. Maybe I can delete this now. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 4, 2, 4, 2, 4, and 4, 4. 4, 4. Okay. And I'll just copy this. 1, 1, 2, 2, 3, 1 and 2. 1 and 2. So you can realize this is the advantage of STAAD and ETABS. They can automate this. Okay, they can automate this. But for me, I intentionally made this as not automated because for educational purpose, that so that learners like for example students can realize the how important the location of the code and its destination going to the S matrix. But you can automate this. Then how many members? We have 5. Loop 1 to 5. Okay, so we have our K. Now for the transformation matrix, okay, all three the girders are horizontal, so this will be R11 should be this. Okay, maybe I'll replace this with this will be R14 because that's a column, right? So I can copy this here and for the 5. So I'll make this R14 and R15. These are the transformation matrix for columns 4 and 5. For girders, I copy this, copy. Then I'll make this 1. Then R13 is also the same. That's it. Then I'm going to loop to 5. Okay. Okay. So we're done with our K. For the to generate the stiffness, loop to 5. Okay, no mistakes at least. So P sub F, where's our P sub F? There, 40 minus 30 minus 30. But remember, our formula is P minus P sub F, right? So P minus P sub F is equal to ST. So we need to incorporate the negative sign. before inverting. So this becomes negative 40, positive 30. Make this 3. Negative 40, positive 30. 30. Okay. So that's our rotation. Okay. So let's now try to, for V1, 1, 2, 3, 4. Yeah. V1 is correct because you only have rotations. QF1, so I'm going to, this is 60, this is 40, 60, negative 40, negative 40. QF2, 60, 30, 60, negative 30. Okay, next is QF3. You can copy this. This is V3, while this is QF3. V3, rotation, rotation. QF3, sorry, I made QF2 should be 66.667. Then 80. This should be 80. Should be 80. 23.33. And negative 60. And then QF3, yeah, 60, 30. 60, negative 30. What else? Okay. So what's the reaction? K1, V1. 60, 40, 60, negative 40. QF2. Mhm. QF4 and QF5. Forgot. D1, D2, D1, D2. This should be D2, D3. D2, D3. Sorry. Should be D2, D3. Then QF4 and QF5. There. So this will be QF. Sorry, we don't have QF4 rather, and QF5. And just make this 0. For V4, this is 0 also. 0, 0, D1. For B5, 0, 0, 0, D2. Right? Should be D2. Okay, you can make this Control C and then paste. This will be Q3, Q3, Q4, 1, 1, 2, 2, 3, 3. Should be 3 also. 3, 3. Then This will be Q4. Okay. Eighty, 60. Maybe I need to correct this. Try this as our formula earlier. Okay, let's now try to check it in STAAD. Okay, then new. Okay, so in STAAD 0, positive 4, and 4, 4. Okay, where's that? Next is 10, 4. Mhm. Next is 10 plus 3, 13, 4. 13, 4. Okay, then add beam. Okay, and then properties, define. Just make this steel so that I think we assume inertia elasticity 200, right? Y point, let's say 0.5 by 0.3. Add close. So we have 2i. So let's define again. This is steel. This now 0.5 and 0.3 times 2, 0.6 to make it 2i. So this is the 2i. Then the rest is I. Okay. Then supports, create fixed and fixed butt. This one is fixed butt. Okay. Next is loading. Add 30, 40. Member load. Negative 30, negative 40, and negative 90. So 30 is here. 40 is here. And 90 is here. But we need 2 meters. Geometry, insert node. Distance of 2, add new point. Okay. Then change cursor to nodal. Okay. Analysis. Analysis commands, add, and close. Did we miss something before we run? Okay, run, save. So, okay, zero errors. Let's check the displacement. Post processing. Press control to exaggerate, right? Okay. Oops. Actually, so theoretically, this has displacement, although it's again very minimal, 0.016 mm. Okay. Next is reactions. What did we get? Okay. So we have 37. Let me check. Where is my... Yeah, so we can expect a discrepancy because again, in actual, there's a displacement. But again, the topic is... Oh, sorry. Where is the share? Resume share, sorry. Okay, that's it. We can... So these are the reactions. There. Then let's compare to our... Here. Where's Q5? I don't have Q5. Q5. Q1, Q2, Q3, Q4. Okay. QC. Control P. Q5. There. Is this in fraction? Q4. Okay, and this. Okay, so I'll let you look for a bit. Okay, so okay, so you see, so Q1, this, remember, this is the vertical and this is the moment, the second one. So I'm getting 33 as moment. STAAD is getting 37. Okay. But remember, we have we have different inertia, right? I typed in 300 in our code. Still, but because we have consistency, this is I, this is 2I, we still follow that consistency. And then this is I, this is I. 33, okay. Then, yeah, but shear 56, 57, I'm getting 54. For, this is member 3. For member 3, so 45 reaction. So I'm getting about 52. Ah, no, no, no. Q1, Q2, Q3. Sorry. 42, sorry. 42. Because this is the right support. 42. Okay, versus 45. For Q4, moment is 6.27. I'm getting negative 6.7. Okay, almost the same. For Q5, uh, by the way, what's his hex? 4.85. I'm getting 5. Okay, 5.04. Almost 5. Okay. For Q5, moment 1.3. I'm getting 3.6, but my shear is negative 2.7, while he got negative 1. Okay. Okay. But at least the signs are consistent. No, this is positive, this is negative. I have here positive, I have here negative. Okay, negative moment, positive moment. I'm get here negative, positive. Okay, that's it. Let's check for the. Mm, maybe I'll check my inertia here because I use 300. What's the actual? 300 by 500. Hmm, 300 by 500 cube over 12. That is 3.125 times 10 raised to 9. No. Times 10 to the negative 9. 3.125. Maybe I'll correct this. 3.125. So to make this twice, 6.25. 3.125. Okay. Okay. So nothing, no, nothing changes much. Okay. Okay. Negative 3. Yeah. Okay. For each member forces, I'll double click this shear bending. Okay. So I have, that's it, 37, 49. Okay. For the moment, while I have here 33, 53. Okay. Then for the shear, 57, 63. I have 55, 65. Okay. Next is here member 2. Oops, sorry. Uh, we're just, let's check the left support. 62 and the shear, same. 63. Okay, I have 64 and 66. Okay. And for the right end here, shear bending 46 And 27. I have, okay, 25, 59. Okay. I don't know. 25. Yeah. 25 is the shear. Okay. Then the bending is, he got 47. I have 59. Okay. Then for member 3, okay, 43. Okay. And the shear 74, which is I have 77, 52. Okay. And then for and 45, the vertical reaction, 42. I obtained 42. For the columns, shear bending, 6, 13, 6 and 13. I have Q4 bending, 6 and 13. They are the same, no, in terms of the column, 6 and 13. Okay. And then shear, 4, yeah, 5. I have here 5 and 5. Almost the same. Okay. And the last one for the column here, shear bending 1 and 3, 1.3 and 2.62. I have here bending, no? 3 and 7. Okay. But for the shear, almost 1. Almost 1. Okay. So that's it. Again, this is just an approximate analysis. No, we assume no, because we assumed no actual deformation, okay, and no sway, okay. But of course, theoretically, uh, there's still a small sway. Here it detects only about 0.001 millimeters. Okay, that's it. Mm. Do you have questions po?